project, I created an autonomous convoy prototype where the biggest contribution is the computer vision algorithm in the tracker vehicle. The lead vehicle is controlled remotely by a human operator. And this is a video of what it looks like. So the tracker vehicle uses a computer vision algorithm that I wrote to track the visual marking, which is the yellow on the lead vehicle, and based on its size and movements and what the computer vision algorithm is reading, it's able to successfully track and follow the lead vehicle, thus creating a convoy. The tracker vehicle is completely autonomous thanks to the computer vision algorithm. So last year, this is a continuation project. Last year I created a more rudimentary version of this, and the whole point of this is to help reduce risk to our troops. While transporting supplies and materials, they're under a great risk of being hit by IEDs and mines and things like that. So I thought it would be so much better if the need for people to be in those convoys was not needed. So the goal was to completely remove the necessity to have humans in the convoy. So this was my engineering goal. So this year I sought to improve the robustness, the tracking error, and the tracking choppiness of the whole convoy. So that meant I had to introduce better computer vision, better motor control, and also use KPIs or key performance indicators to evaluate and compare my algorithms. The KPIs were the robustness, the tracking error. Robustness is simply the percentage of completed runs. So out of 10 runs, how many did it complete, and I turn that into percentages. And then tracking error is the median Hausdorff distance of trajectories. So that's how far away the trajectories were from each other over the course of their run. And the tracking choppiness is a standard deviation of vehicle distances, so how much the distances from each other varied over time. This is how I did my experiment. So I set up a bird's eye view camera mounted on the ceiling fan, so right there, as you can see, a little tripod. And on the staging ground, I'd set the lead and the tracker vehicle on their course. So I would set an autopilot mode for the lead vehicle, so I'd have repeatability in my trial. So pre-made autopilot, two of them in fact, one a simple turn and one more complex turn. So then I would record the runs for each algorithm, and I'd keep 3 of the runs and put them in a MATLAB analysis program where I'd compute the KPIs, so the robustness, the tracking error, and the tracking choppiness. And then based on what I observed and what the numbers gave me, I could make changes to my computer vision algorithm and to the convoy in general. And this is kind of what it looks like when I extract all the data out of the videos. So you can see the 2 trajectories, the cyan and the white. So for example, right here, that's how I find the standard deviation distance over time, so how much it varied over time. As you can see, that distance, it varies over time. And then the median Hausdorff distance, so how far the trajectories were away from each other, and that's in very small amounts, so a couple millimeters. And then using, because I measured the staging ground, I can convert that into centimeters. Okay, I get the data in pixels and I convert it into millimeters. And this is how the algorithm evolved, and the new vision algorithm, which is the main contribution. I'll first explain the how it works. So off a sensitive line on the camera's phone, I can read all the pixel values that I get off the image, and then I can mark it as yellow found, so whether it found a yellow or not. And where it did find yellow, I mark it as a 1, and I mark where it didn't as a 0. then I can find the pixel to pixel jump. So it's gonna jump from 0 to 1, and then from 1 to 0. And then those I can mark as the strongest positive and negative jumps, thus giving me the size, so the width, and the center of the visual marking. And based on its width, so as it comes closer, it's going to get wider. As it goes farther, it's going to get thinner. And the center moves left and right. So based on those things, I can compare the center and the width to thresholds, and I can decide whether to turn left, right, and so forth. So let me explain these graphs a bit because they're slightly confusing. So I have 3 axes. So the first axis is going to be the algorithm number. So I have 4 algorithms. Algorithm 0 was last year's algorithm, where I started off from this year. Algorithm 1 is the first new one, so first improved. Algorithm 2 is the second improved, and algorithm 3 is the state of the art, the one that I'm using right now. And then we have 2 autopilot modes. The purple right here is a simple turn, and the orange is going to be a harder, stronger, more complex turn. And then here we have what I was looking for. So for example, percentage of completed runs, I want that to be, of course, as high as possible, so at 100%. Tracking error, we want error to be low, so as low as possible, that's good. And tracking choppiness, same thing. I don't want a choppy ride, so the lower the better. So last year's algorithm, it actually performed pretty well in terms of tracking error and tracking choppiness, but the robustness was kind of low. So that was due to the computer vision system not tracking the old visual marking well. So after I introduced a new visual marking with color, and I added color sensitivity to the computer vision system, the robustness went up to 90%, which is great, but sadly the tracking error and the tracking choppiness went up too because the motor control wasn't synced up very well. So after that was fixed, I brought the tracking error and the tracking choppiness down and robustness to 100%. After that happened, I tested it for a stronger autopilot, so the harder one, and I got the robustness was good, tracking error was good, but the tracking choppiness, the ride was kind of choppy, so I introduced an averaging system of all the results, and I was able to bring that to an all-time low as well. So at the end, everything performed very well. And I just want to leave with you guys how I would scale this up. So on a scaled up, more realistic version, I would have a wider range camera, a better camera at that as well, faster processors, and similar things, just bringing the whole Convoy from a small Lego model to a more realistic, actual real world example. And this has applications everywhere. So not just in military, but in mining, in agriculture, and even commercial transport. Anywhere where there's a convoy, this can be replaced to reduce human error and the necessity to even have humans present.
Bravo. Good job.
Excellent.